Alright, so in this example, we're again going to be given some curve. In this case, it's y equals sine of x divided by 1 minus cosine of x. And we're asked to identify what is the tangent line to this thing at the point pi 0. And this is a problem that we've seen a few times. It's come up a few different sections, and the process is always the exact same. To find this tangent line, I'm going to need to know a point, which I know it's going to be pi 0. And I need to know the slope of this line. And we know the slope of this line is going to be connected to the derivative of this function evaluated at pi. In this case, what I need is really the big thing that I need. The point is easy enough to find. But what I'm interested is my slope is going to be my derivative evaluated at pi. And that's the big step in this one, is I actually have to differentiate this kind of giant quotient of trig functions and then ultimately evaluate that thing at pi. And so let's go ahead and see if we can actually differentiate this thing. In this case, I'm going to have y prime, which is the derivative with respect to x of my giant expression, which is sine of x divided by 1 minus cosine of x. You can see right away that this thing is a giant quotient, so the quotient rule should be screaming at you. This idea that I'm going to differentiate this thing by using this giant, huge quotient rule. What's going to be involved is I'm going to have to differentiate a sine as well as a cosine, but we know how to do both of those, so actually differentiating this thing is not so bad. What I'm going to get is I'm going to get the low term, which is a 1 minus a cosine of x, multiplied by the derivative of the top part, which is just simply a sine of x. I'm subtracting, in this case, the top part, or the high term, multiplied by the derivative of the bottom, which is a 1 minus cosine of x. And I'm taking all of that, and I'm dividing it by a 1 minus cosine of x quantity squared. Alright, let's go ahead and see if we can actually differentiate this stuff. I'm going to have a 1 minus cosine of x. The derivative of sine is going to be a cosine, which is going to, you can see already that I'm going to get some cosine squared, so I might have some kind of nice stuff occurring. What else do I get? I have a negative sine of x, and I'm going to differentiate 1 minus cosine of x. The derivative of 1 is a 0, and the derivative of cosine is going to be a negative sine, but I have actually another negative sign in this case. So when I differentiate a negative cosine of x, I actually get a positive sine of x. And then it's going to be all over a 1 minus a cosine of x quantity squared. Okay, let's just rehash all this to make sure we're kind of on board with the right stuff and whatnot. I differentiated this giant quotient, this low term, multiplied by the derivative of the high term, and then I'm subtracting off the high term multiplied by the derivative of the low, all over the low term squared. Differentiating sine is going to give me a cosine, and differentiating a 1 minus cosine, the derivative of 1 is a 0, and the derivative of negative cosine of x is going to give me a positive sine of x. Okay, what you can see here is I'm going to differentiate, or I should distribute my cosine of x in this case, giving me a cosine of x, a negative cosine squared of x, and I'm going to have a negative sine squared of x. All of that divided by a 1 minus cosine of x quantity squared. And when we're here, we actually could evaluate this thing at pi. Ultimately, all I have to do is just find the derivative at pi. But I do want to know what this thing looks like. This actually does clean up a little bit nicer. And just kind of as practice to work with these derivatives to try to make them look as nice as possible, I'm going to do a couple extra steps to actually show that this thing does clean up a little bit better. What I'm going to do is I'm going to use this fact that cosine squared plus sine squared is equal to 1, which tells me that negative cosine squared minus a sine squared is actually equal to negative 1. And that's going to give me a cosine of x with a negative 1 up on top, and then a 1 minus a cosine of x quantity squared on the bottom. In this case, what I just used is I used that cosine of x plus a sine squared of x is going to equal a 1. Multiplying everything through by a negative sign gives me a negative cosine squared of x. A negative sine squared of x is equal to a negative 1. Oh, lost some of my sign. And that's exactly where that little negative 1 comes from. At this stage, you can actually see that there's some similarities between the top and the bottom terms, but everything is off by a negative sign. So I'm going to go ahead and just flip this to the next page. I'm going to differentiate this case of a sine of x divided by a 1 minus cosine of x. What we had from the previous page is that this is equal to a cosine of x with a negative 1 over a negative 1 cosine of x quantity squared. You can see that the top and the bottom, like I said, are very similar. They're just off by a negative. If I factor a negative sign out of the top, what I'm left with is a negative cosine of x and a positive 1, and writing that in kind of the other order is going to look like this. And then I have the exact same expression on the bottom. And the important thing to see here is that this expression 1 minus cosine appears on the top and on the bottom, which actually gives me that this thing simplifies to a negative 1 all over a 1 minus cosine of x, which is a really nice compact derivative in this case. It's very nice to see that this giant kind of fraction, which we know explodes using this quotient rule, actually does in fact collect to something that's not nearly as gross. In this case, it's just simply a negative 1 divided by 1 minus cosine of x. What I want to do then is I'm viewing this thing as my y prime. I want to evaluate this thing actually at pi, telling me that y prime of pi is going to be a negative 1 over a 1 minus a cosine of pi, which gives me a negative 1 up on top, a 1. Cosine of pi is actually a negative 1, so I actually have a double negative down here, leaving me with a negative 1 all over 2. And that's exactly what my slope is in this case, is a negative 1/2. Once I have that, the rest of the problem is pretty easy. My line in this case is simply a y minus a y1 equals m x minus x1, plugging in everything that I know in this case. I know what my slope is, a negative 1/2. I have my point, dump all of this stuff in, kind of see if I can clean up my line a little bit. Ultimately, I have a y minus a y1, which is 0, equals a negative 1/2 because that's my slope. And then I'm going to have a negative, or x minus a negative pi in this case. Which you can see I don't actually have to bring anything over for the y. I already have y equals. I'm just going to distribute that negative 1/2, giving me a negative 1/2 x, and then there's a positive pi over 2. In this case, my line has a slope of negative 1/2, and it actually has a y-intercept in this case of pi over 2.